Every wrench in every toolbox in America is cut to a standard that no American ever set. Not Congress, not the Bureau of Standards, not any committee that ever met in Washington. The length of the American inch, the number governing every rifle barrel, every engine block, every aircraft fastener manufactured in the United States, was fixed by a firearms inspector from a factory town in central Sweden, working alone at a bench in his own house, on a lathe he made out of his wife's sewing machine. He settled it in 1912. Washington did not make it official until 1959. What nobody understood at the time was that by then there was nothing left to decide. Industry had been running on his number for 47 years. This is Trade Archive. If you build things, measure things, or make your living inside a tolerance, hit that like button and subscribe. We cover the machines, the companies, and the men who made modern manufacturing possible. But this story does not begin in Sweden. It begins with a problem that sounds trivial until you actually try to solve it, and then it becomes one of the hardest problems in the history of manufacturing. How do you make something flat? Not approximately flat. Flat to a standard you can prove, and prove again tomorrow, and prove again in another country, in another century, on a machine nobody has built yet. Here is the trap. To make a flat surface, you need to check it against something already flat. To make a straight edge, you need a straight edge. Every measuring tool in a modern shop was made by a machine that was itself set up using a measuring tool, which was made by an earlier machine, set up with an earlier tool. Follow that chain backwards far enough and you arrive at a place where there is nothing to check against. No reference, no master, no authority. Just a man with a piece of iron and a problem. The answer is one of the most elegant pieces of reasoning in the history of the trades, and it requires exactly 3 pieces of iron. Take 3 cast iron plates. Call them A, B, and C. Work A against B, and both surfaces will improve, but they will improve toward each other. If A goes slightly hollow, B goes slightly domed, and they will mate perfectly while being perfectly wrong. 2 plates can lie to each other forever. 3 cannot. Bring in the 3rd plate and work them in rotation. A against B, B against C, C against A, and the lie has nowhere to hide. The only shape 3 surfaces can all share, mutually, is a plane. That is the bootstrap. No external reference required. From nothing but 3 lumps of iron, abrasive, and an enormous amount of patience, you generate the first true flat surface in the world, and every dimension in modern industry descends from it. Now, the version of this story that circulates online usually credits Henry Maudslay, and Maudslay deserves a great deal. He ran the most important machine shop in London at the turn of the 19th century. He trained half the men who would build the Victorian machine tool industry, and he treated the surface plate as the first datum in the shop, the thing everything else got referred back to. He worked flats down to about 1/1000th of an inch, which in 1800 was extraordinary. But the method, as it is actually practiced, belongs to his student. In 1840, Joseph Whitworth published a paper titled On Plane Metallic Surfaces and the Proper Mode of Preparing Them, and Whitworth's contribution was not the 3 plates. It was abandoning grinding entirely. Grinding embeds abrasive in the iron. The plate keeps cutting after you stop, and it wears whatever touches it. Whitworth's answer was to coat 1 plate with a thin film of pigment, press the second against it, and read the transfer. Where the color lifts, metal is high. Then remove that metal by hand, with a scraper, in flakes measured in millionths. Bluing, scraping, testing, scraping again. It is slow, it is brutal on the hands, and it improved achievable flatness by roughly a factor of 100 over what Maudslay had managed. It is also worth saying plainly, because the men who actually do this work will say it in the comments anyway, that the 3-plate method is not automatic. Strict rotation alone can converge on a saddle, a surface that is hollow in one direction and domed in the other, while every pair still reads as matched. Getting a true plane requires reversal, and it requires reading the bluing correctly. It is a skill, not a procedure. Whitworth then did something that made the point impossible to ignore. He built a measuring machine that resolved to 1/1,000,000th of an inch and demonstrated it publicly, including at the Great Exhibition of 1851 and to the Institution of Mechanical Engineers in 1859. The machine was sensitive enough that a 1-inch iron bar held between the anvils would visibly grow when a man touched it with his finger. Body heat. That is the entire margin. So, by the middle of the 19th century, the flat plane was solved. Everything was in place. What the industry did not yet grasp was what everything was building toward, because a perfectly flat surface will tell you that two things are the same. It will not tell you how long either of them is. For that, you need a unit. And units, at that point in history, were a catastrophe. Consider what an inch actually was. English law defined it through the composition of yards and perches, a statute of genuinely uncertain date, usually placed around the year 1300, and attributed variously to Edward I or Edward II. The record does not settle it. The statute holds that 3 grains of barley, dry and round, laid end to end, make an inch. Before you laugh at that, check your shoes. British and American shoe sizing still increments in barley corns. 1 full size is 1/3 of an inch, a half size is 1/6, and the formula was codified in that form around 1856. You are standing in a medieval grain measurement right now. The problem is obvious the moment you try to use it. My barley is not your barley. My barley in August is not my barley in November. And the same disease had infected every trading nation in Europe. In France, before the Revolution, the historian Ken Alder documents roughly 250,000 distinct units of weight and measure in use across the kingdom. Not 250,000 measurements. 250,000 units. The livre weighed 489 grams in Paris and 403 grams in Pernay-les-Fontaines. Same word. Same country, 20% difference. Every contract across a provincial boundary was a negotiation about vocabulary before it was a negotiation about price. Britain tried to solve it with physics. The Weights and Measures Act of 1824 defined the imperial standard yard against a physical bar, but Parliament understood that bars can be lost, so they wrote in a restoration clause. If the standard were ever destroyed, it could be rebuilt from a pendulum, specifically a pendulum beating seconds, in the latitude of London, in a vacuum, at the level of the sea. That pendulum was legislated to stand to the yard in the ratio of 39.1393 inches to 36. It was a beautiful idea. Anchor the yard to the rotation of the earth and the pull of gravity, and no fire, no theft, no war can ever take it from you. 10 years later, on the night of the 16th of October, 1834, the Palace of Westminster caught fire. The immediate cause was a stove in the House of Lords that had been loaded all day with the Exchequer's obsolete wooden tally sticks. It became the largest fire in London between the Great Fire of 1666 and the Blitz. The imperial standards burned with the building. So Britain went to the Restoration Clause and found that the clause did not work. The pendulum reduction had errors in it, and worse, the underlying premise was wrong. A seconds pendulum is not the same length everywhere because gravity is not uniform across the Earth. It varies with latitude, with altitude, with the density of the rock beneath your feet. The natural, universal, reproducible standard was not universal and not reproducible. They rebuilt the yard the only way left to them. From surviving copies, referred back to a bar made by John Bird in 1760 and legalized as new bronze line standards under the Act of 1855. Bronze number 1 became the yard. And then the metrologists noticed something that should have ended the whole philosophy of physical standards on the spot. The bronze yard was getting shorter. Slowly, invisibly, the alloy was changing over decades and measured against the French meter, The British yard was shrinking. By the 1890s, the two great English-speaking nations had drifted measurably apart. America fixed its yard at 0.9144018 meters. Britain fixed its yard at 0.9143993 meters, a gap of about 2 parts per million. Because while London was rebuilding a burnt bar from copies of a copy, Paris had already attempted something far more radical and had very nearly gotten 2 men killed doing it. The French decided that if a unit was going to be arbitrary, it should at least be arbitrary about something permanent. Not a king's arm, not a grain of barley. The planet. The meter would be defined as 1/10,000,000th of the distance from the North Pole to the equator, measured along the meridian that runs through Paris. Nobody knew that distance. So in 1791, the Academy of Sciences commissioned 2 astronomers to go and measure it. Jean-Baptiste Delambre would survey the northern arc from Dunkirk down to Rodez. Pierre Méchain would take the southern arc from Rodez to Barcelona. Triangulation, station by station, across the length of France. The Academy estimated the work would take under a year. They began in June of 1792. By September, France was a republic. Within a year, it was the Terror. Picture the position these 2 men were in. They are traveling the countryside with crates of gleaming brass instruments, climbing church towers and hilltops in a nation where church towers are being pulled down, lighting signal fires at night on high ground so their partner can take a bearing. To a village committee hunting for royalists and foreign agents, that is not science. That is signaling to the enemy. Both men were detained. Their papers, signed by an academy that the Republic had abolished, were worth nothing. McCain was seriously injured in an accident in Spain and spent months unable to work. The survey took 7 years. And in the winter of 1793 in Barcelona, McCain took his latitude readings from 2 different stations and got 2 answers that did not agree. The discrepancy was small. It was also, by the standards of the work he was doing, impossible. It meant one set of observations was wrong, and he could not determine which. He did not report it. He carried that number privately for the next 11 years, revising and re-revising his data, refusing to publish, sinking into a depression that colleagues recorded but could not explain. In 1804, he returned to Spain to try to resolve it and died there of yellow fever. Delambre inherited the notebooks. He found the discrepancy immediately. And he made a decision that historians have argued about ever since. He suppressed it, writing that he would leave out details that might diminish confidence in the mission. Here is what makes that decision land. McCain's concealed error was not actually the problem. In 2019, a paper in the Journal of Geodesy modeled the whole survey against modern satellite data and put the final shortfall in the meter at 197 micrometers. About 0.2 of a millimeter. But the analysis assigned roughly 95% of that error not to McCain and not to bad surveying, but to a factor 18th century geodesy had no way to account for: the local gravity field bending the plumb lines that every latitude observation depended on. Under 2% came from measurement error. About 3% came from an incorrect assumption about the flattening of the Earth. The true quarter meridian is 10,002,290 meters. They were aiming at 10 million. They missed by roughly 1.5 miles spread across a quarter of the planet, and the unit that governs almost all of modern science has been that fraction short ever since. McCain destroyed himself over an error he did not cause and could not have prevented. What the French tried to do next explains why the metric system feels the way it does. They did not stop at length. The circle was recut from 360 degrees to 400, so that 100 kilometers would equal exactly 1 unit of latitude. The day was decimalized in 1793 into 10 hours of 100 minutes of 100 seconds and actually entered official use in 1794. It lasted about 2 years. The angle survived in surveying. Decimal time did not. But the length held, and in 1799, the meter was fixed and legislated. France then spent 40 years refusing to use it. Napoleon reintroduced customary units for everyday trade in 1812, and metric was only made compulsory again in 1840. Which tells you something durable about standards. Legislating one is easy. Getting a nation of shopkeepers to adopt one is a different problem entirely, and it is the problem this entire story is really about. In 1875, 17 nations signed the Convention du Mètre, and the International Bureau at Sèvres produced roughly 30 prototype bars in an alloy of 90% platinum and 10% iridium. The cross-section was Henri Tresca's design, an X, and the reason for that shape is the kind of detail that separates people who make standards from people who talk about them. The X is stiff for its weight and comes to temperature quickly, but the real trick is that it places the graduation lines on the neutral axis. The bar can sag under its own weight between supports, and the marks do not move. They engineered the sag out of the definition. The United States received National Prototype Meter number 27, along with number 21 as a working copy. Number 27 was unpacked with ceremony at the Executive Mansion in front of President Benjamin Harrison, and it became the physical foundation of American length. Then, on the 5th of April, 1893, Thomas Mendenhall, Superintendent of Weights and Measures, issued the order that ends the argument. The meter and the kilogram became the fundamental standards of the United States. The yard was defined as 3,600 over 3,937 of a meter, which makes the American inch 25.4000508 millimeters, not 25.4, a hair over. And across the Atlantic, the British inch, running off that slowly shrinking bronze yard, came out at 25.39998 millimeters, a hair under, 2 parts per million. On a 1-inch part, that is 50 millionths of an inch of disagreement, which sounds like nothing until you are building interchangeable parts in 2 countries and assembling them into the same machine. Nobody was going to fix it either. Fixing it meant one nation publicly conceding its inch was wrong, and no Bureau of Standards on Earth was going to volunteer for that. It took someone with no standing in the argument at all. By 1896, in Eskilstuna, a steel town about 100 kilometers west of Stockholm, a 32-year-old inspector at the Carl Gustaf rifle factory had a workflow problem. Carl Edvard Johansson had been born in 1864 in Örebro County, emigrated to Minnesota as a teenager, studied there, and come home in 1884. His job at the rifle factory was inspection. The factory was building weapons under foreign license, and every time the design changed, every dimension needed a gauge, a fixed piece of steel that either fits the part or does not. Fixed gauges have obvious problems. They wear. They are slow to make. Change a design and you need an entirely new set, and until those gauges exist, production stops. Johansson's calculation was that a full set of individual gauges for a new rifle would take years and cost more than the contract. His alternative was a set of blocks. Rectangular, hardened steel, each one lapped to a precise thickness, sized so that a small number of them stacked together could produce an enormous number of dimensions. Instead of 1,000 gauges, 1 box. He roughed the blocks at the factory. He finished them at home, on his wife's sewing machine, which he had fitted with a grinding wheel and a treadle-driven lap. The first set was completed in 1896, 102 blocks, covering 0.5 millimeter to 300 millimeters in steps of 1/100th of a millimeter. His Swedish patent followed in 1901. He founded C.E. Johansson AB in Eskilstuna in 1911. The blocks did something nobody had designed them to do. Slide 2 of them together, face to face, with a slight twisting pressure, and they stick. Not magnetically. They will hang there, defying gravity, and pulling them apart takes real force. At a mechanical engineering conference in Stockholm in 1917, Johansson demonstrated it by suspending more than 90 kilograms of weights from the lower block of a rung pair. The bond was calculated as equivalent to about 33 atmospheres of pressure across the contact faces. Machinists call it ringing, and there is a persistent myth that nobody knows why it happens. That is not quite true, and it is worth being accurate about. Per the NIST Gauge Block Handbook, the mechanism is understood in outline. A molecularly thin film of oil or adsorbed water, on the order of 25 nanometers, forms a capillary bridge between two surfaces flat enough to exclude essentially all air, and short-range molecular adhesion does the rest. It is not atmospheric pressure, because blocks ring in a vacuum. It is not cold welding. What remains genuinely debated is the relative weight of each contribution, not the phenomenon itself. The surfaces are simply flat enough that the ordinary rules stop applying. Now to the part that matters most, and the part the popular version of this story consistently gets wrong. In 1912, Johansson began manufacturing gauge blocks in inch sizes for the English-speaking market, which forced him to answer a question no government had been willing to answer: which inch? The American inch was 25.4000508 millimeters. The British inch was 25.39998. He could not make two product lines. So he split the difference and cut his blocks to a nominal 25.4 millimeters exactly, a value within a few parts per million of both official definitions and identical to neither. He did this in 1912. Not, as the story is often told, later under Ford. 11 years before he ever met Henry Ford, an inspector in a Swedish factory town picked a number because it was convenient for manufacturing and shipped it. And because everyone who cared about precision bought his blocks, and because every gauge in every shop was set against those blocks, and every part was cut to those gauges, industry quietly stopped using its legal inch and started using his. It acquired a name: the industrial inch. Trade associations formalized it in Britain in 1930 and in the United States in 1933. The Bureau of Standards documented the situation in a report in 1936. The de facto standard had overtaken the de jure standard, and the law spent the next quarter century catching up. The First World War is where the blocks became strategic. According to Goran Ahlström's academic study of Johansson's business, drawing on Torsten Althen's 1948 biography, it was decided in 1915 that the Johansson system would be the norm for American firms, civil and military, producing war material. His biographer notes, with what he himself concedes is some exaggeration, that the blocks won the war. There is a much better story attached to this period. A U.S. sales manager pulled out of the army, sent into Sweden through the German submarine blockade, smuggling 128 sets past inspectors. It is a terrific story. It also does not appear in any primary archive or scholarly source I could find, and it traces most plausibly to a popular and fairly worshipful 1945 book about mass production. Treat it as folklore. The documented part is that the War Department standardized on a Swedish inspector's blocks, and that supply from a neutral country in a naval war was a genuine strategic exposure. The post-war depression nearly finished him. Orders collapsed, and Johansson approached Henry Ford, who bought the American company in 1923 and brought Johansson to Dearborn. Ford devoted real space to the blocks in his 1931 book, Moving Forward, written with Samuel Crowther. He describes the Johansson gauge department as the nearest approach to absolute exactness in the entire operation, controlling the gauges across all Ford industries, and he states the consequence in the only terms that matter on a production floor. A limit of 3/10,000ths of an inch became common. On a few parts, they held 1/10 of a thousandth. Understand what that unlocks. Gauges can now be checked against a master multiple times per shift. Drift gets caught before it becomes scrap. A part cut in one plant fits an assembly in another. Interchangeability stops being an aspiration and becomes a routine industrial fact, and the entire economics of mass production follow from it. The reckoning arrived after that war. when the inch-using allies discovered that parts manufactured to their respective national inches were not reliably interchangeable. There were at least 3 working definitions in circulation. Canada legislated first, in 1951, fixing the inch at 25.4 millimeters exactly. Then in 1959, the United States, the United Kingdom, Canada, Australia, New Zealand, and South Africa signed the International Yard and Pound Agreement. The yard became 0.9144 meters. The inch became 25.4 millimeters. Exactly Johansson's number. 6 national governments, 3 decades of committee work, and the answer was the compromise a Swedish inspector had picked in 1912 for the practical reason that he only wanted to run 1 production line. He did not live to see it ratified. Carl Edvard Johansson died in Eskilstuna on the 30th of September, 1943, 16 years before the signatures. What his blocks left behind is the thing that actually holds modern industry together, and it has a name most people outside the trade have never heard. Traceability. A gauge block in a shop is checked against a better block. That block is certified by an accredited laboratory. That laboratory's masters are certified against national standards held by NIST or NPL in Britain, or their equivalents in every industrial country, and each link in that chain is documented with a stated uncertainty. Not, we compared it to something good. A written, unbroken, uncertainty quantified chain from the part in your hand back to the definition of the meter, which is no longer a bar in a vault. In 1960, the meter was redefined against the wavelength of krypton 86. In 1983, it was redefined again as the distance light travels in a vacuum in 1/299,792,458th of a second, which fixes the speed of light by definition and makes the meter reproducible in any properly equipped laboratory on Earth. The 2019 revision of the S1 restated it in the same terms. The dream of 1791, a unit anyone, anywhere, could recreate from nature, took 192 years and required a laser, but it arrived. The United States kept one artifact of the old fight until very recently. The survey foot, about 2 parts per million longer than the international foot, survived in land surveying because rebaselining every property boundary in the country was not worth the trouble. It was finally retired at the end of 2022. The last living fragment of that 2-part per million disagreement outlasted Johansson by 79 years. And the blocks themselves? A set of gauge blocks with a traceable calibration certificate now costs less than a decent cordless drill. It buys you tool room grade rather than laboratory grade, and a metrologist would want to know which grade before letting it near a master. But the accuracy that once existed only in a Swedish workshop is now a routine purchase for anyone with a garage and an interest. Johansson's first sets, by contrast, cost more than most of the men who needed them earned in a year. Go back to those 3 plates of iron. No reference, no master, nothing to check against, just the geometric fact that 3 surfaces cannot all lie to each other at once. That is where this began, with the recognition that precision does not have to come from somewhere higher up. It can be generated from nothing, by people willing to do the work, and then handed forward. Everything after that was the same problem at a larger scale. Delambre and Mechane trying to fix a unit to the planet itself and getting it wrong by 0.2 of a millimeter because the ground beneath their instruments pulled harder in some places than others. Parliament writing a pendulum into law as insurance and watching the insurance fail. A Swedish inspector picking a number because it simplified his tooling, and 6 governments ratifying it half a century later because the world had already moved in. The tolerance you work to today was not handed down by an authority. It was bootstrapped, argued over, burned in a fire, hidden in a dead man's notebook, and finally settled by a man at a sewing machine who was mostly trying to avoid making 2 versions of the same product. Whatever you are cutting this week, something in your shop traces back to that box of blocks.